Welcome to the Cloud Native Container Networking in AWS using CNI plugin session. Obviously, I went for the buzzword bingo here. I tried my best to shove in service mesh and Envoy in there to make it cooler, but I failed. Uh, on a serious note, I know it's late in the day, there's the party to go to, and some of you are jet lagged, including myself, and I really appreciate your patience and interest in attending this session. We spent a good part of last year making the container networking story better on AWS, and I hope to share some of these requirements, the design choices we had, and how we implemented these using CNI plugins in the session. So a bit of introduction about myself. My name is Anirudh Aithal. I'm an engineer in the Elastic Container Services team. My immediate team mostly focuses on the container execution environment in ECS. So this includes the container runtime. We have an ECS agent that manages the state of containers. We also have a number of networking plugins, including the CNI plugins that are the focus of today's session. My team maintains most of that. You can find me on GitHub and Twitter on my alias. So the agenda for today is mostly covering the CNI plugins that we wrote for the VPC, Amazon VPC, which is the software-defined networking solution if you're running in the AWS cloud. So I'm going to make certain assumptions that some of you are already at least have heard some of these terms. Before that, I would like to go a little bit into the primitives that make up both container networking and VPC. But as with everything in Amazon, the biggest thing I want to share with you today is the requirements that our customers came to us with, and how, even though these requirements are not new for containers, containers certainly exacerbate the need for some of these primitives that our customers are looking for. So in our customer conversations, we heard requirements that could be mostly put into three different buckets. The first one is usability. So whatever networking solution that we were going to provide had to be super easy to use and super easy to integrate with. So what this means is, as developers, all you need to say is my application needs networking, and my application needs to communicate with this other set of applications, and that should be it. You should be able to use the same abstractions in the cloud as you use when you're developing code. And as an infrastructure provider or a network administrator, you should be able to say that you should be able to integrate with whatever solution we were providing and bring in your own custom interfaces or higher level constructs or higher level abstractions on top of these things. For example, if you want to bring in your own software-defined load balancer solution, you should be able to do that. If you wanted to bring in your own service discovery solution, you should be able to do that. And service discovery is also an interesting example for the next set of requirements, which is containers need to communicate with each other. I'm going to use the word container interchangeably with pod in Kubernetes and task in ECS. So containers need to essentially, or applications need to essentially discover each other and communicate with each other using their IP addresses, which hopefully are natively routable. This means that the IP address that you give the container, it has to be routable from whatever top of the rack switch or the router that you maintain. The next set of requirements were around security. Security is something that our customers care about deeply, and our tenet is being secured by default. So what does this mean? It means that container A should be able to isolate its traffic from container B, in the sense that container B shouldn't be able to snoop on or influence the pattern of container A. And even from a processor running on the host. So if you have a rogue process on the host, even that should not be able to mess up with your container's traffic. The next part of this is access control, being able to enforce network policies by a network administrator rather than at a user level makes it a lot more secure environment to work with. For example, I, as a network administrator, care really about the fact that none of the containers will respond to any traffic on port 22 or port 80, something like that. So being able to describe this at the network administrator level was also something that was very important to our customers. The next one is being able to audit that whatever policies you have enforced are actually taking place on these instances. So how do you check that you can enforce these policies and being able to get alerts when these policies are not being enforced? The last one is being able to have a scalable performance solution which doesn't fall over when you go from 100 containers to 100,000 containers or even to 1,000,000 containers. So just because you have more endpoints to deal with doesn't mean that your networking solution should fall over. Similarly, you shouldn't suffer any performance regression in terms of higher latencies, lower bandwidth, just because you have more endpoints in your network. And the last one is monitoring. So being able to identify hotspots and address them in an automated manner, being able to identify bottlenecks is also something that our customers brought up as a pain point. There's also another aspect here. Even if we as a network solutions provider can't provide this solution, we should provide you the abstraction so that you can build your own solution on top of this. So extensible in a way also comes into this picture. So with these requirements in mind, let's look at how traditionally applications have been able to network with each other. So in this example, I have a HTTP daemon process. It's listening on port 80, let's assume that. It's bound to the default networking interface or H0. The outer box is an EC2 instance. This can be a host or a virtual machine, whatever translates with you the best. The default network interface also has an IP address, but before the packet actually reaches the H0 interface, it goes through some of the routing rules, routing table, applies some of the rules, and you also have netfilter in Linux, which is applying firewall rules. Using the IP tables command is typically how you interact with it. So all of these together, including the local host interface, form what you call a networking stack. So if you zoom in a little bit, what's actually happening underneath is all of these networking resources are present in the default network namespace. So namespaces are a construct in Linux where you can create logical copies of a particular resource. Network namespaces let you create logical copies of the networking resource. And by default, all processes inherit namespace from their parent, which is why HTTP daemon, which is a child of the init process, has access to all the networking resources that init process has access to. So if you run more processes on this host, all of them can discover each other using the local host interface because they're all sharing this default network namespace. Containers change this paradigm where you can have multiple network namespaces and have processes belong to these namespaces. So by default, these namespaces are isolated from each other. So if I wanted to run two HTTP daemons on one host, I would instead create a container, and the second HTTP daemon is running within the container, and the first one is running in the default namespace. So now I essentially have two HTTP daemons running on the same host, and I didn't have to change the port number on which these processes were listening on, because that's the other alternative solution, right? If I want to run 3 HTTP daemons on the default namespace, I essentially have to change the port numbers, and that's not a scalable solution or a manageable solution. So now we have this new container. It has its own network namespace. There's a HTTP daemon running within it, but it's still not connected to anything. So how do you connect namespaces together? You use something called virtual Ethernet pairs or VETH pairs in Linux. VETH pairs establish a tunnel or a pipe between two network namespaces. They look, act, and feel like Ethernet devices, but they always exist in pairs. So here we have one end of the VETH pair, which is VEC1, connected to the other end, which is VEC1 peer, and both of them have IP addresses associated with them. And the VE-C1 pair actually belongs to an overlay. This can also be a bridge or a NAT. I'm using the term overlay in a generic sense here. And you have a connection from this overlay to the H0 interface. And now this HTTPD container can receive traffic from the internet or wherever this endpoint is connected to using this V8 pairs. So if we zoom out a little bit more, this is a scenario in which you have multiple containers running in multiple instances. So again, this you can replace virtual machine or host for this instance. But the underlying thing here is these containers are connected with each other using an overlay network. So in an overlay network, you have generally some sort of a proxy running in the default namespace that knows how to communicate with container 1. The same proxy also runs here, knows how to communicate with container 2. Proxies maintain the state of the world. They do the address translation, packet forwarding, and everything. So in the world of overlay networking, let's look at how packets usually traverse. So here, C1 wants to send a packet to C2, and the very first hop for the packet is the virtual Ethernet pair, and the next hop for the packet is the overlay network, which is the virtual Ethernet device, the peer of the one on which the packet was sent from. And then something interesting happens. The proxy will still forward the packet through H0, and then eventually the packet ends up on the other host, assuming these two hosts are connected. And then, And then the packet, the proxy that's running here, the overlays data plane component forwards the packet to the virtual Ethernet pair, and then it eventually ends up on the destination container. So this process took roughly 5 hops. Depending on your overlay solution, this could be less or more. Some providers have lesser number of hops because they optimize on some routes, others do not. So how did this overlay solution fit into our requirements? So we were still working with very simple abstractions. Discovery was still easy because all the containers were getting native IP addresses, but we lost on security, and we lost big time because all of the traffic in this was flowing through this H0 on this host and being received through H0 on this host. Isolation was very hard for us to do. And the same reason is why access control was also very hard for us to do, because when you have traffic from multiple streams exiting and entering through one network interface, you can't essentially enforce access control rules at a finer granularity. Also, because overlays have to maintain the state of the world all the time, and if one of the components die, they are usually not highly scalable, although some vendors do have solutions that do really scale well. And we suffered big time on performance as well, because all of the traffic is flowing through one endpoint. There's a single point of failure, and this means that it's constricted both at a network path, and also if something bad happens to that network interface, then all of the containers lose their network connectivity. So we went back, looked at how EC2 instances are networked, and see if we can get any inspiration from this. So this is a typical EC2 instance setup. We have VPC, which stands for Virtual Private Cloud, which is a software-defined network. All customers get one in AWS. And VPC usually has a large IP address range. It's almost like your data center networking. And you have, so by default, it gets a /16 range, which means you can create 65,535 endpoints within it. And then a VPC can be carved out into multiple subnets. Subnets are a network partition construct in VPC, and you can associate a subnet with an availability zone. Availability zone are a reliability construct in AWS where logically grouped data centers are partitioned together into an availability zone. If your application runs in multiple availability zones, even if one of these subnets go down, the other subnet will be up and you won't suffer downtime. So in this example, we have two subnets. They have /20 seeders. The large VPC, you can assume, has a /16 seeder, and you have instance 1 and instance 2. There's also this thing called security group, which is a VPC level construct where you can enforce access control policies using firewall rules. So you can say which IP addresses uh, are allowed to communicate with these instances and which ports are exposed. You can also block ports, and you can also do traffic shaping using these routing tables, which are also a VPC level construct. And our customers are already used to this. So, and VPC essentially creates this illusion of a flat network. So VPC itself is kind of acting like an overlay. So in this diagram, if we send a packet from instance 1 to instance 2, it's pretty straightforward. Packet exits instance 1, and it just shows up in instance 2. So there's no additional hops, there's no performance penalty or anything, because VPC essentially has this notion of a flat network. So this is very appealing to us, and we wanted to see what made this so magical and if we can leverage the same thing for our containers. So under the hood, each EC2 instance essentially gets a virtual network interface card, which is also called an elastic network interface or an ENI. And all ENIs in a VPC are networked together. There's no additional performance penalty for communicating between two ENIs. And each EC2 instance by default gets one ENI. And the interesting thing here is you can create ENIs on demand and associate multiple ENIs to an instance. So that's what essentially led to the solution that we eventually implemented, which was creating ENIs for tasks or pods. So around November last year, we released two CNI plugins, the ECS CNI plugin and the VPC CNI plugin for Kubernetes, both of which essentially do the same thing. You can find the source code and design details on GitHub. There's detailed design documents with workflows and everything for both of these plugins. The central idea for both of these plugins is the same. Each container or each task or each pod gets its own ENI. The ENI gets provisioned on demand. And because so this brings the same level of abstraction to EC2 instances to containers. So containers are now a first-class networking primitive with these features. And because they have an ENI per application, discovery is very simple as well. So if you look at the diagram now, instead of any overlay, there's no overlay. Here, a container 1 has a ENI. This container has an ENI as well. And all of these are for part of the same VPC. So network traffic communication in this world is pretty straightforward. Container 1 wants to send a packet to container 2. It knows the container 2's IP address. This IP address is natively addressable within the VPC. And the packet just ends up on the other container. So no extra hops, no performance penalty. You can enforce security group rules. So you can actually enforce firewall rules at a network administrator layer rather than at an application layer. There's no additional state for us to maintain because VPC does all of the IP address management. So overall, it turns out to be a pretty simple solution for our customers to use. So if we look back at the requirements, we achieved on-demand delivery because we are treating network as a resource constraint for our scheduler to do the placement on. Discovery is pretty simple because we're using native IP addresses. You have isolation from network namespaces. You can enforce access control policies using security groups. You have audit logs from VPC flow logs. So if you haven't used VPC flow logs before, it's a pretty cool feature. It lets you essentially do a TCP dump kind of a semantic on your VPC. So you can at real time see what interface is sending what traffic to what endpoint and get alerts based on that. So CNI for us was a vehicle to do the instance implementation for all of these things. And it really helped us a lot because our implementation for these plugins was using CNI, which meant that our solution weren't restricted to a container orchestrator. So as long as your orchestrator knew how to how to integrate with CNI, you could use use our plugins with any network orchestrator. In fact, our VPC CNI plugin, which was optimized for ECS, is being used by at least 2 customers on Kubernetes and vice versa. So let's look at some of the design constraints or design decisions that we had to make. The very first one was, should we do CNI or should we do CNM? So CNM, if you're not aware, was still a thing 2 years ago. This Docker's networking model. In this model, you still write plugins, but Docker daemon integrates with these plugins instead of the orchestrator. And your plugins are running as long-running daemons, whereas in CNI, they're short-lived executables. So we had 4 major axes on which we were trying to decide which route to take. So the most important thing for us is being minimally intrusive to containers lifecycle. So what this means is that if our orchestrator dies for whatever reason, we don't want that to affect the availability of our container and its traffic. So containers should still be able to function normally from a networking perspective if the plugin dies. And we don't want to be in the business of managing the lifecycle of these plugins themselves, because then you will have to write a supervising process, which makes it even more complicated. And if you're running a daemon, rolling out upgrades is also a real pain, because you need to drain things, and then you need to shut things down, then you need to install a new version, then you need to bring the new version back up and maintain its health. So we didn't want to be in any of that business, and CNI plugins fit right into that requirement, because CNI plugins are just short-lived executables. They come, provision, and then they go away. And the second aspect was simplicity. So CNI has a specification against which you can actually write reliable and repeatable tests. So this means that you have a consistent interface to program against, which was also a big plus for us. And CNI plugins are actually chainable. So they're great in terms of extensibility. Our customers can extend networking solution on their own, or it makes us easy to extend our networking solution for them, because CNI has this chained execution. It's almost like working with a Linux shell. You can pipe the result of one plugin to another plugin, and it still works. And the last one is ecosystem support. libcni, which is the library against which all CNI users integrate with. So kubelet, ECS agent integrate with libcni, is battle tested. Multiple customers already use it in production, and that was a great thing for us. So here's a brief, just to illustrate how simple it is to use CNI plugins. This is a sequence diagram of how CNI plugins are invoked. So CNI plugins essentially respect 2 verbs, add and delete. And you just invoke the add command with a networking config, or you invoke the delete command with a networking config. Add creates the network, delete tears down the network. And it's as simple as that. In this diagram, I actually have 2 plugins. But if you have just one plugin, even the last part goes away. And it's 2 arrows, which is pretty much a dream for anybody who is programming against it. The next aspect was which programming language to use, Golang or something else. We chose Golang because of its support for static binaries. Installing static binaries is much simpler to installing third-party packages on which your binary depends on, and so on. And you can also package this into a container. So it was a default programming language for us to use. Again, the ecosystem support is something worth noting here as well. libcni is pretty mature and is written in Go. So it's pretty much a no-brainer that we would use Go. I do know some people who have written plugins in Rust, but I don't say hi to them that often. Next is packaging and distribution. We package the plugin as in a Docker container, which means that we get all of the advantage of packaging containers, packaging advantages that containers give you. Here's an example of a Docker file. You can find this in our repo for how we actually package these plugins. They get copied along with the ECS agent binary, or if you're running the Kubernetes flavor of it, they get deployed as daemon sets. And all of this is made possible and much easier because we are packaging them as containers. Another thing here, even if you're not writing a CNI plugin, is just a good software practice, is to version your executables and version them especially with the Git hash from which they were built. Because when you're deploying these things at scale, when you have hundreds of thousands of copies of these running, if there's any problems, it's very easy to determine which build caused the issue. So we have human readable version numbers, but we also have Git short hashes. And we actually automate this version by using build flags in Go. So Go has this concept of build flags where you can inject constants into your binaries. And when these binaries are built, they take the version information. And then when you run the -- version command on these plugins, they just emit the sort of information we saw in the previous slide. So, excuse me. So versioning everything in an automated manner is something that I would highly encourage you do in whatever software system you're building. Next, testing the plugins. We actually have close to 100% unit test coverage. Not that it guarantees absence of bugs, but it's great to have that sort of coverage. We also run integration tests and end-to-end tests in our CI/CD pipelines. So if you remember Dan Cohn's keynote from yesterday, CI is something that you should deeply care about if you don't already. And our end-to-end tests actually create a ENI, provision it for a container, alert us if there's any issues, and they're great at detecting regression or any such problems very early on in our development process. So just to conclude, avoid feature envy for containers. Bring in the same abstraction as you have for virtual machines, at least in terms of networking, because it makes a lot of things very simple. And we're really grateful to authors of the CNI plugins because it's an awesome project for anyone to integrate with, and it made our lives a lot simpler. And version everything with Git shas. It helps you a lot when you're dealing with a distributed, complicated application to detect what actually caused the issue. So here's some related links in case you're downloading the slide on the internet or something. There's the Netlink library, the CNI project are all great resources, not just for using, but also looking at how to write good maintainable Golang code. So I would highly encourage you to read that. And with that, it's a wrap. Thanks for your time. You can reach me or our team on GitHub using these links. And yeah, thanks again. I guess we have time for questions if anybody has questions. Yes. I don't know if you have a mic or anything. I couldn't hear you at all. I'm sorry. Okay. Yes. Mm-hmm. Yeah. So the question is, what's the provisioning latency for ENIs if you're provisioning an ENI for each pod? We actually have a daemon set that provisions ENIs ahead of time for the pod. So when the instance starts up, we provision as many ENIs as we can. So the initial provisioning latency, you only take a hit when the instance starts. So the containers themselves don't see this performance hit. Mhm. Yeah. The question is, there's a limit on the number of ENIs that you can attach to an instance. Does it limit the number of pods? Yes, it does. And it's something that we are working on to increase behind the scenes with our networking team. If you're using pods, we also optimize it by creating secondary IP addresses for ENIs. So that helps it a bit, but not a whole lot. But yes, that's something that we are aware of and we are working on. Yes. Mhm. Right. So the question is, how do you apply cluster level access control policies as a network administrator? So you can create a security group at a cluster level. And when you're creating your instances, you can tell them to inherit from that security group and then have it be applied in that manner. Uh, Also, I think you can use vendors like Cilium and one more that I can't recall, Flannel, who also have such provisions. If you're using like the BGP version of a plugin, you can enforce policies at your router level as well. Yes. Uh-huh. So the question is, how production ready is this? Because you're using other providers and you want to switch to it. It's actually production ready. We released this back in October last year, and the ECS version of it is actually being used in production a lot by our customers. The Kubernetes version of it was built with our partners, and some of them are already using it in their in the EKS preview. But you can use it, of course, outside of the EKS product as well in your own cluster. We think it's pretty production ready. If you find any issues, do reach out to us on GitHub. Yeah. Yes. The question is, do ENI support public IPs? The secondary ENIs do not support public IP addresses. It's a feature request that we've heard often from our customers. Uh, but we haven't arrived at if they should really support public IP addresses, because public IP addresses have both security concerns and there's also IP exhaustion concerns. So we do want to provide some sort of public IP addressing scheme. We don't know if it's essentially going to be IPv4 or IPv6. Yes. The question is, if I want my cluster to span regions, will VPC peering work? And the answer is, it should work in theory, but I would also question your motive for spanning regions in a cluster. But it should be doable. VPC peering does allow it, and it, I think, is one of the use cases for customers using that. So as long as the ENIs are created in the proper region, it should just work. Yes. Yeah. The question is, are these CNIs registerable as targets to ALBs and ELBs? The answer is yes. And that's why we went with the ENI route, because we wanted integrations at as many places and layers as possible. If you wanted to use service discovery using Route 53, you should be able to register these as targets. If you're using load balancers, you should be able to register these as targets. And they are registerable as targets. Yes. Mhm. The question is, the previous attempts to do this have involved modifying routing tables, and there's limits to how many entries are there in a routing table. Is this going to hit similar limits? The answer is, routing table still has a limit of 50 entries, but this will not hit that limit because all ENIs in a VPC are addressable with respect to each other just because they belong to a VPC. And like the very first rule you see in the routing table says use local. So all of them should be able to just utilize that and communicate with each other. They do have to be part of the subnets that are carved out of the VPCs. Yes. Yes. The question is, if we're using secondary IP addresses, will the load balancer still be able to use the ENI as a target? In theory, I think it should be possible because if you use the network load balancer, it uses the IP address and port as a target. So it should be doable, but I haven't tried it myself, so I can't say for sure. Come talk to me after the session. I'm at the AWS booth, and we can hash it out. So you had a question, sir. Can you please elaborate what's cluster? Mhm. So when you say global IP, is it the elastic IP? Is it the elastic IP that you're referring to? Yeah. So the question is, if my service has an elastic IP address, will it still work with ENIs? The answer is yes. Elastic IP addresses are also a VPC level construct. So any VPC level abstraction that works with traditional EC2 instances will work with this solution. That's it? Oh, one more. Yes. Right. So the question is, what's preventing a rogue process from just randomly creating and provisioning ENIs on a host? And there's security concerns with that. I agree with that security concern. Uh, the answer here is to run your provisioning process in as part of your API server or in ECS. It's happening at a scheduler layer. So only the scheduler is privileged to create ENIs, and whatever components are on the host can just use these ENIs. So they get the information that this pod or this task should use this ENI, and then they provision it. So as long as you constrict the only the provisioning part of the network to the plugin, you should be safe. That's it. Okay, awesome. Thank you.